Earth's rotation period relative to the Sun. Its mean solar day is 86,400 seconds of mean solar time, 86,400.0025 SI seconds. Because Earth's solar day is now slightly longer than it was during the 19th century due to tidal deceleration, each day varies between 0 and 2 sims longer. Earth's rotation period relative to the fixed stars, called its stellar day by the International Earth Rotation and Reference Systems Service, IERS, is 86,164.0989 seconds of mean solar time, UT1, or 23H56M4.0989s. Earth's rotation period relative to the precessing or moving mean vernal equinox, misnamed its sidereal day, is 86,164.0905 seconds of mean solar time, UT1, 23H56M4.0905s. Thus the sidereal day is shorter than the stellar day by about 8.4 ms. The length of the mean solar day in SI seconds is available from the IERS for the periods 1623-2005 and 1962-2005. Apart from meteors within the atmosphere and low-orbiting satellites, the main apparent motion of celestial bodies in Earth's sky is to the west at a rate of 15 degrees/h equals 15/min. For bodies near the celestial equator, this is equivalent to an apparent diameter of the Sun or the Moon every 2 minutes. From Earth's surface, the apparent sizes of the Sun and the Moon are approximately the same. Earth orbits the Sun at an average distance of about 150 million km, 93 million mi, every 365.2564 mean solar days, or 1 sidereal year. This gives an apparent movement of the Sun eastward with respect to the stars at a rate of about 1 degree/day, which is 1 apparent Sun or Moon diameter every 12 hours. Due to this motion, on average it takes 24 hours a solar day for Earth to complete a full rotation about its axis so that the Sun returns to the meridian. The orbital speed of Earth averages about 29.78 km/s, 107,200 km/h, 66,600 mph, which is fast enough to travel a distance equal to Earth's diameter, about 12,742 km, 7,918 mi, in 7 minutes, and the distance to the Moon, 384,000 km, 239,000 mi, in about 3.5 hours. The Moon and Earth orbit a common barycenter every 27.32 days relative to the background stars. When combined with the Earth-Moon system's common orbit around the Sun, the period of the synodic month, from new moon to new moon, is 29.53 days. Viewed from the celestial North Pole, the motion of Earth, the Moon, and their axial rotations are all counterclockwise. Viewed from a vantage point above the north poles of both the Sun and Earth, Earth orbits in a counterclockwise direction about the Sunday. The orbital and axial planes are not precisely aligned. Earth's axis is tilted some 23.44 degrees from the perpendicular to the Earth-Sun plane, the ecliptic, and the Earth-Moon plane is tilted up to plus or minus 5.1 degrees against the Earth-Sun plane. Without this tilt, there would be an eclipse every 2 weeks, alternating between lunar eclipses and solar eclipses. The Hill sphere, or the sphere of gravitational influence, of the Earth is about 1.5 million km, 930,000 mi, in radius 181 n20. This is the maximum distance at which the Earth's gravitational influence is stronger than the more distant Sun and planets. Objects must orbit the Earth within this radius, or they can become unbound by the gravitational perturbation of the Sunday. Earth, along with the Solar System, is situated in the Milky Way and orbits about 28,000 light-years from its center. It is about 20 light-years above the galactic plane in the Orion Arm. The axial tilt of the Earth is approximately 23.439281 degrees with the axis of its orbit plane, always pointing towards the celestial poles. Due to Earth's axial tilt, the amount of sunlight reaching any given point on the surface varies over the course of the year. This causes the seasonal change in climate, with summer in the northern hemisphere occurring when the Tropic of Cancer is facing the Sun, and winter taking place when the Tropic of Capricorn in the southern hemisphere faces the Sunday. During the summer, the day lasts longer, and the sun climbs higher in the sky. In winter, the climate becomes cooler and the days shorter. In northern temperate latitudes, the sun rises north of true east during the summer solstice, and sets north of true west, reversing in the winter. The sun rises south of true east in the summer for the southern temperate zone and sets south of true west. Above the Arctic Circle, an extreme case is reached where there is no daylight at all for part of the year, up to 6 months at the North Pole itself, a polar night. In the southern hemisphere, the situation is exactly reversed, with the South Pole oriented opposite the direction of the North Pole. 6 months later, this pole will experience a midnight sun, a day of 24 hours, again reversing with the South Pole. By astronomical convention, the 4 seasons can be determined by the solstices, the points in the orbit of maximum axial tilt toward or away from the Sun, and the equinoxes, when the direction of the tilt and the direction to the Sun are perpendicular. In the northern hemisphere, winter solstice currently occurs around December 21st, summer solstice is near June 21st, spring equinox is around March 20th, and autumnal equinox is about 22 or September 23rd. In the southern hemisphere, the situation is reversed, with the summer and winter solstices exchanged and the spring and autumnal equinox dates swapped. The angle of Earth's axial tilt is relatively stable over long periods of time. Its axial tilt does undergo nutation, a slight, irregular motion with a main period of 18.6 years. The orientation, rather than the angle, of Earth's axis also changes over time, precessing around in a complete circle over each 25,800-year cycle. This precession is the reason for the difference between a sidereal year and a tropical year. Both of these motions are caused by the varying attraction of the Sun and the Moon on Earth's equatorial bulge. The poles also migrate a few meters across Earth's surface. This polar motion has multiple, cyclical components, which collectively are termed quasi-periodic motion. In addition to an annual component to this motion, there is a 14-month cycle called the Chandler wobble. Earth's rotational velocity also varies in a phenomenon known as length of day variation. In modern times, Earth's perihelion occurs around January 3rd, and its aphelion around July 4th. These dates change over time due to precession and other orbital factors, which follow cyclical patterns known as Milankovitch cycles. The changing Earth-Sun distance causes an increase of about 6.9% in solar energy reaching Earth at perihelion relative to aphelion. Because the southern hemisphere is tilted toward the Sun at about the same time that Earth reaches the closest approach to the Sun, the southern hemisphere receives slightly more energy from the Sun than does the northern over the course of a year. This effect is much less significant than the total energy change due to the axial tilt, and most of the excess energy is absorbed by the higher proportion of water in the southern hemisphere. A study from 2016 suggested that Planet 9 tilted all the planets of the solar system, including Earth, by about 6 degrees.